All right. So if you're watching this video today, we took this quiz called Chapter 11 vocab for practice. It's not on your grade. So the three of you that are gone, four of you, if you watch it, that's what we did. Feel free to take it. Okay, looking down here. Ooh, adhesive. These are tricky. Attractive forces between unlike. Heat of fusion, hydrogen bonding, critical pressure, dipole, normal boiling point. Well, good. Phase diagram, we haven't studied those yet, but probably not that hard to figure out. Triple point, kind of confusing. Intermolecular force. We were only there. Oh my. And ion dipole. So adhesive, that looks like our lowest one. Okay. I would study these because raise your hands if you've done no effort to study them actively. And I'm not mad, but I was just trying to make you stop hitting the claps is what I was trying. You guys are freaks, absolute freaks.
By the end of the class,
I spent 2 minutes on the quiz.
31%. Oh boy. Okay, you should study. That's my feedback. Okay, moving on.
I have no idea what I got wrong.
Oh, 19,000.
20. 20.
You guys are nerds.
I'm 2,005.
Okay, here we go. I think if you just did it on one with two fingers, you do it faster. Oh my gosh. This is embarrassing that you guys know like the cadence you got to do to get claps on GimKit. That's where we are as a society. You don't care about your grade. Okay. Okay, chapter 11 wrap up. Here we are. Did we talk about vapor pressure yesterday, Friday? We did? Okay, so vapor pressure is the amount of gas above a liquid, and it is determined by the substance temperature and the intermolecular forces. The stronger IMF, the what vapor pressure? Lower, whoops, vapor pressure. Everyone, whether you're clapping or not, you're going to be held accountable for that knowledge right there. If the liquid has strong intermolecular forces, it will have a lower vapor pressure, meaning less of it evaporates. So there's less gas above the liquid. And you definitely should know the inverse of that. The weaker the intermolecular forces, the greater the vapor pressure. All right, I need to go back this way. We had these. So we're on volatility, which we were talking about it right when the bell rang, and like we measured that as how easy it is for something to evaporate, right? Not its explosivity. It's how easily it evaporates. So gas is very volatile, and we think that means gasoline is going to blow up, right? But what it means really is that gasoline makes a vapor very easily. And the vapor is what burns in gas. Right. And don't do this, but like I did it, I thought it'd be really cool. One time I had to drain my gasoline out of my lawnmower, or was it my snowblower? I don't remember, but it was freezing cold when I did it. And it was in a garbage can. And I thought, this is gonna be the coolest thing. I'm gonna light this on fire. And I backed up and I threw a match in there, and the gasoline put the match out. That's all it did. And I threw like 10 more in there. I'm like, well, what is this? Well, what was the problem? It was too cold. There wasn't enough vapor above the gas to actually light on fire, or above liquid, I mean. Okay, now do not test that at home, ever, ever. Don't. No. Okay. So the stronger, look at me, the stronger the intermolecular forces, the lower the volatility. So we'd say gasoline must have what type of intermolecular forces?
or no.
Weaker, because it is very volatile. The intermolecular forces, the lower the volatility. Okay. They're like almost exactly the same thing. Now they are different, but you can explain their changes in exactly the same way. Finally got warm enough. When I showed up this morning, it was 50.5 degrees in this room. And I'm a man that doesn't like cold anymore. So I bundle up. Okay, next we have surface tension. No, we have, surface tension. You learned surface tension forever ago when you put drops of water on a penny. Did you do that in second grade or whatever? Or you floated the paperclip? Or you've seen like what I called water skeeters or the Jesus bug, all right? Okay, what? No, we're not. Okay. So how do you drown those skeeters? What we call it as kids. What? No. We would go to the ditch and we'd put Dawn dish soap, a couple drops, and they're all like, boom. I was a monster as a child. It was just so cool to watch. Like they can walk on water. Bloop. No, they can't. They can die. All right. Well, what does the Dawn do? It breaks the surface tension. The bug floats there, or the water holds together, or the paperclip floats because water is attracted to itself. And definitely not to dish soap. What? It doesn't want anything else. It sticks together. What dish soap does is it goes between and it severs the intermolecular forces. Not 100%, but it lowers them a ton. It breaks the surface tension down. Now, soap is not made to do that, but soap is a non-polar substance. Because most of the stuff we get stuck on our food, it is either ionic or non-polar. Because we like salts and sugars, all right? And then we like fats. And so to clean a dish, if it doesn't just come out with hot water, we use soap, which breaks apart the substances that goes into the water and lowers the intermolecular forces. All right, so surface tension. The higher the intermolecular force, the greater the surface tension, which should make sense. If they're holding on tighter, it takes more effort to break them. How are we doing? Are we in the 30,000 range yet? Oh man, this is what a day. Hopefully Abby's enjoying this at home. Sorry if you're watching this on tape delay, humans. You'll never get the satisfaction of clapping in this stupid GimKit program. Okay, viscosity. Right? You've probably never heard of this word, have you? You have?
Yeah, I've only heard it in the context of molasses.
Okay. When I was a kid, there was an oil called STP, which now to us it means something else. But they'd have commercials. Yeah. And I don't remember, it was like Standard Petroleum, I think is what STP stood for. Anyway, their commercial would say that their oil prevented viscosity and thermal breakdown. You're like, well, what does that even mean? Well, viscosity is the ability of a liquid to flow. So that's why you hear it with molasses or syrup or oil that you put into your engine. You want all those things to be able to flow. And molasses, the colder it is, the slower it goes. Same with everything else. That's a super good question. Molasses has a very low viscosity. If it doesn't move, it's low. So viscosity, the higher the viscosity, the greater the flow rate. This is only liquids. Okay, so it's its ability to flow. I have a whole slide for viscosity right here. So resistance of a liquid to flow is called viscosity. It's related to the ease in which molecules can move past each other. Viscosity increases with stronger intermolecular forces. So I said it backwards, I guess. Even I said it backwards. Because this says viscosity increases with stronger intermolecular forces and decreases with higher temperature. So it's its resistance. I should have just come to this slide. It's not its ability to flow, it's a measure of the resistance of it to flow. So high viscosity would mean then that it doesn't flow well. I apologize. So we would say that these substances here, we have hexane, heptane, octane, nonane, and decane. And their viscosities are listed right here. And so let me write them as normal numbers. So 0.1233326 is this value. And 0.12142 is this value. So this is a much larger atom right here, or molecule, sorry. So what we know about its, not Vesper, it's whatever I'm looking for, van der Waals forces. What do we know about this compared to that? Bigger. It is easily polarized, or it's more polarizable, right? Versus hexane, which it is. Hexane's a liquid at room temperature. This is probably a liquid, but a really viscous one. You okay with that? So the stronger the intermolecular forces, the more it resists flowing. Yes. And water would basically have 0. Which, I mean, not 0, but a lot of decimal places. Well, oil typically, well, it depends on what you mean by what oil. It's more viscous than water. Yes, Seth. It does. Yeah, I said it wrong at first. Okay, we good? Viscosity is hardly ever tested, so we're not going to spend a ton of time on that one. Heat of vaporization, which is the energy required to boil a substance, to turn its liquid into a gas. That's what vaporization is. So this is very similar to its boiling point. So the stronger the intermolecular forces, the blank heat of vaporization, higher or greater. Okay, so it's just like boiling. If they hold each other stronger, it's harder to break them. If it's harder to break them, it means it needs more energy. Yep. All right, let me see what I got here. Okay, so there's those bugs. And yep, it was sad that I would do that. But like, I grew up in Vernal from like 0 to 11. And Vernal, you had hay fields, cornfields, and canals, and a ditch. That was my life. And across the street, the ditch widened out to like 4 feet wide, and it got kind of deep. So we threw probably like 8 metric tons of rocks in that. Okay, and then we would chill in it all summer, and the bugs would be there, and we're like, "Ooh, someone go get dish soap," and they'd like all be pulled up like in this little corner trying to avoid us. The ditch kind of went like this, and they'd be right here. There's a little eddy, nice and slow water, where all the leeches were also. Okay, and you would just like drop soap right here, and then pretty soon just see you bugs. Go swim with the leeches. Yeah, we got lots of leeches. It was fine. You just pull them off. What? Yeah, hundreds of times. You go like this. Ouch. That's about it. Then you have a little circle of blood. It's life. You lived in a ditch. It's like literally what we did. Yeah.
Why do people like movies and everything?
Because they're sissies. They didn't grow up playing in a ditch. Anyone else grow up playing in a ditch? My only worry in my life was make sure I didn't go through the culvert and die. Like that was my only stress in life. Yep. Okay. Phase change. All right. There's just a couple of nuggets left in this chapter. They don't seem to fit in, but they fit in. So we should probably do a clap check. Here we go. Oh, 67,000. What?
Just for a little bit longer.
No, I know why. Tim, grow up.
I'm a child.
Oh my gosh.
Okay.
Just behind.
These kids are 12. Yeah. I would hate to be a girl. Like, you're gonna have to marry one of these. I was never this immature.
I would marry one of these.
Put that over there. Nope. I'm never going back. Never. Okay. We just talked about the heat of fusion. All of you are gonna get carpal tunnel. All right.
I'm on fire.
So, energy required to change a solid at its melting point to a liquid. Oh, we just talked about vaporization. Sorry. This is fusion. So fusion is when we go from solid to a liquid, and that is this purple part. Now, you don't need to know these quantities. You need to know how to compare them. What do you think the blue part is? Heat of vaporization. What you have to be able to do is explain why this is significantly smaller of a value than this is. So we have fusion and vaporization. Why on earth would it take way more energy to vaporize something than to melt it? Okay, it takes a lot more heat for what? So you move them faster, that's true, but they're moving faster from solid to liquid also. And break apart every intermolecular force. Think about what vaporization does. It takes a liquid and turns it into an ideal gas. So it takes much more energy to break, I don't know why I put it, whatever, every intermolecular force. When we go from a solid to a liquid, we've sort of reduced the IMFs to a point where the atoms or molecules are allowed to move. But for vaporization, they're gone. So it takes significantly more energy to sever every intermolecular attraction than it does just to make them movable. Okay, you don't have to know these numbers at all, but you have to be able to explain this. Okay, vapor pressure, we already talked about. Okay, here's what the AP test wants you to know about changes in properties or changes into a different substance. They require an exchange of energy. This is not hard. It's saying if you're going to change it from a solid, liquid, or a gas, or reverse it, you have to give it energy or remove energy. Okay, so there's a lot of words here, but energy must be transferred to a system to cause a substance to melt or boil. You should know that. We have to add heat, right? The energy of the system therefore increases as the system undergoes a solid to liquid or liquid to gas phase transition. You should be okay with that. The more heat you add, the more energy you have. So if it went from a liquid, which was medium, to a gas, which was high, obviously the energy increased, the temperature increased. Likewise, a system releases energy when it freezes or condenses. The energy of the system decreases as the system undergoes a liquid to solid, gas, whatever. The temperature of a pure substance remains constant during a phase change. This may be the only thing that's even remotely new to you, and it is important. My wife and I have fought about this for years. If you had me for normal chemistry, you have heard this before. And this is still a problem. Like to this very weekend, my wife was cooking chicken Alfredo, which I love, and so I didn't really get mad. But for the 20 millionth time of our marriage, the boiling water overflowed, like it bubbled over the top. That happens to me about once every 10 years, and to her like every day. Because my wife thinks she'll cook the food faster if we leave it on high. But I bring it to a boil and then turn it way low to simmer, because that's what the directions say. All right. And I also know that whether something's like boiling vigorously or it's just boiling a little bit, it's the same temperature. Because listen, anything above 100 degrees Celsius does what? It leaves, it evaporates, which means this liquid cannot ever get higher than 100 degrees. It can't. Okay. Now I lost it like 15 years ago, and I took home like my electronic probe and I connected it to the computer and I like put it in here and I like put it in one of these and I said, look, it's the same temperature. It's 96 point something degrees no matter what. And so you can turn it down. And you know what she said?
No.
She said, nope. She said, well, then the bubbles cook it faster.
What's your rebuttal to that?
So I feel like you have to wait till it's vigorous.
No. So if anyone can think of a science experiment to prove that bubbles don't cook food, please let me know, because I have not been able to win this conversation.
I've got it.
Bubble, like the soap bubble, if you explode them on the food.
Well, that
No, because those aren't the same.
she's like, she just thinks the bubbles are like that they're hot, which is true, and that's helping it cook faster. But I just, I love her.
So you just look at it there, see if it's faster.
Maybe. Okay, now this whole story right here in this sentence is illustrated in this picture right here. This is an important picture to grasp. It's an important picture to be able to draw and to label. And what's important is your ability to explain each segment on this. It is not hard because you learned this in multiple grades before. But A to B in this segment, I hear some talking and I'm getting slightly annoyed. In segment A to B, what is happening? What are we doing? All right, warming. I'm going to write heating because I already had it. We're heating a solid. Okay, so this is for water, but it could be for really anything. Well, not anything, because some of them are jacked, but whatever. Here we go. When we add energy, because that's what we're doing, we're adding energy, the temperature of a solid increases. Well, duh. Okay, but then it gets a little bit tricky. So this just, we put energy in, temperature rises. But then we get B to C and the temperature remains constant. So how do we understand or explain what's happening in BC? Phase change. And we know now that during phase change, the temperature of the substance does not rise. Because the energy, we're still putting energy in. That's what's mind-boggling about this. But the energy at this point is going into loosening up this solid structure into a liquid instead of heating its temperature. So it was rigid, and then all of a sudden we get to a certain point, and now we're going to loosen these and break them apart. Okay, that energy is there. Now, this line right here is not very long compared to this one, right? And that's, we should know what's coming up. Okay, segment C to D. What's happening there? Heating liquid. You all right with that? Okay, this is kind of cool. Oh, I don't have one today. Usually I'm ready for this moment. When you go to wherever you go to get a drink, you put ice in here and it will stay a certain temperature for hours. It doesn't rise. Now, if you leave it still, the top gets warm and the cold's cold. But overall, it stays constant because all that energy until the ice is gone is going into what? Melting the ice. So that's why your cup with ice in it stays the same temperature the entire time. But the moment all the ice is gone, now what happens? Now the temperature rises quickly. So like 4th of July, your drink was cold, 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 and then really warm in not a very long period of time. And that's because all the ice left and now all the heat goes to raising the temperature. All right, kind of cool. All right, then D to E, we must be doing what? All right, we're phase change, we're boiling. I don't know what happens. It does that every once in a while. So we have D to E, which is the phase change, and you must absolutely be able, well, I had to do that, that was annoying. Be able to explain why D to E is greater. Why is it happening? I am not touching it and it was rolling. All right, so vaporization is the breaking of all intermolecular forces between molecules. And in exchange, all that energy goes in, sends them all out, and then after it's all gas, then we'll heat the temperature. All right, so E to F, I won't write it, but that's just raising the temperature of a gas by adding heat. Fair enough.
Is there another phase change ever?
There's plasma. We don't talk about plasma in chemistry. That's when we get so hot that we strip the electrons and all we have are nuclei. What's that? The sparks? Yeah. Mhm. It looks, no, but they look like a spark. Go ahead. Burning the water. Well, it would decompose into hydrogen and oxygen, then keep heating it so hot that the electrons fly off. And then we see that light process as plasma. Okay, I think you only care about one thing now.
I'm at 95. 95,000.
I'm winning there.
I'm beating you. Until the bell rings, until the bell rings.
Stop it. We must end the same.
All right. I think we're done. Abby, sorry that was a waste of time mostly, but you're amazing.